大家好，我们今天的影片呢，我们是来做微软2023年年度的那个针对开发人员的大会哦 ，Microsoft Build， 它其中有一个 session 的一个活动，一个 session 办完的影片摘录。这个影片摘录的内容是 State of GPT 哦 ，GPT 的现状的报告，是由一位 Andrej Karpathy， 他是 OpenAI 的创办成员之一，以及他也是 OpenAI 现任的研究员。他针对这方面来做针对 GPT 的一些蛮独到的看法。我们认为这个影片内容含金量很高，所以我们把它做成我们针对一部分内容做摘要。那接下来是这个影片摘要内容，影片完整的网址我们在画面下面，然后我们也会放在 YouTube 频道的叙述里面哈，所以这些内容呢，我们会这样做：我们把这个影片的内容全部就是上中文的字幕，然后演讲者的内容我们会采用每5分钟播放，然后才一段加上我们的旁白的中文解说。我们每5分钟我们做一段解说了哈，然后影片的内容我们只有节录。Android 其实它这个影片里面有讲怎么样去建置一个大型语言模型，以及怎么使用啦哈。我们只针对怎么使用的部分来做节录。
So this is number. Having said all that, these are kind of like the assistant models that are probably available to you at this point. There's a team at Berkeley that ranked a lot of the available assistant models and gave them basically ELO ratings. So currently some of the best models, of course, are GPT-4 by far, I would say. Followed by Claude, GPT 3.5, and then a number of models. Some of these might be available as weights, like Vicuna, Koala, etc. And the first 3 rows here are all RLHF models, and all of the other models, to my knowledge, are SFT models, I believe.
接下来是第一段的内容的解说。在第一段里面呢，我们解录到是这样，就是说 Android 它对于那个商用的，就是可以付费使用的大型语言模型目前它上面的影片里面看起来有点时间差。我们拿到在一个大型语言模型有从 UC 伯克莱大学，他们有成立一个网站，就是画面下面这个网址看起来是每隔2个礼拜会针对这些大型语言模型，尤其是聊天方面的，一直来做 PK。做排行，所以现在最新的排行看起来是这样：第1名是 GPT-4， 就是 OpenAI 的 GPT 的最新的版本，目前商用的最新的版本。第2名跟第3名呢，看起来其实换了看起来是那个 Anthropic， 那是有另外一家那个 AI 方面的公司，他们所做的2个语言模型叫 Cloud， 它看起来占据的商用的第2跟第3名，那第4名才是GPT 3.5 就是 OpenAI 现在免费让大家提供的聊天的界面，看起来掉到第4名。开源的部分呢，也有3个名次就是在这个网页上的排行榜。那这3个语言模型里面呢，其中有蛮多个都可以进行中文的聊天对话的那未来我们可能要开资源我们公司看看能不能试试看，去帮大家在这方面多做一些探索。所以这个领域其实变化的非常的快，不管是商用的跟开源 Open Source 其实都一直的名次或者是相关的提供出来的方案跟内容都一直在变化当中。
Okay, so that's how we train these models on a high level. Now I'm going to switch gears and let's look at how we can best apply a GPT assistant model to your problems. Now, I would like to work in a setting of a concrete example. So let's work with a concrete example here. Let's say that you are working on an article or a blog post, and you're going to write this sentence at the end. California's population is 53 times that of Alaska. So for some reason, you want to compare the populations of these 2 states. Think about the rich internal monologue and tool use and how much work actually goes computationally in your brain to generate this one final sentence. So here's maybe what that could look like in your brain. Okay, for this next step, let me compare these 2 populations. Okay, first I'm going to obviously need to get both of these populations. Now, I know that I probably don't know these populations off the top of my head. So I'm kind of like aware of what I know or don't know of my self-knowledge, right? So I do some tool use, and I go to Wikipedia, and I look up California's population and Alaska's population. Now I know that I should divide the 2, but again, I know that dividing 39.2 by 0.74 is very unlikely to succeed. That's not the kind of thing that I can do in my head. And so therefore, I'm going to rely on a calculator. So I'm going to use a calculator, punch it in, and see that the output is roughly 53. And then maybe I do some reflection and sanity checks in my brain. So does 53 make sense? Well, that's quite a large fraction, but then California is the most populous state, so maybe that looks okay. So then I have all the information I might need, and now I get to the sort of creative portion of writing. So I might start to write something like, California has 53 x times greater, and then I think to myself, that's actually like really awkward phrasing, so let me actually delete that, and let me try again. And so as I'm writing, I have this separate process almost inspecting what I'm writing and judging whether it looks good or not. And then maybe I delete, and maybe I reframe it, and then maybe I'm happy with what comes out. So basically, long story short, a ton happens under the hood in terms of your internal monologue when you create sentences like this. But what does a sentence like this look like when we are training a GPT on it? From GPT's perspective, this is just a sequence of tokens. So a GPT, when it's reading or generating these tokens, it just goes chunk, 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 chunk. And each chunk is roughly the same amount of computational work for each token. And these transformers are not very shallow networks. They have about 80 layers of reasoning, but 80 is still not like too much. And so this transformer is going to do its best to imitate, but of course, the process here looks very, very different from the process that you took. So in particular, in our final artifacts, in the data sets that we create and then eventually feed to LLMs, all of that internal dialogue is completely stripped. And unlike you, the GPT will look at every single token and spend the same amount of compute on every one of them. And so you can't expect it to actually you can't expect it to sort of do too much work per token. So, and also in particular, basically these transformers are just like token simulators. So they don't know what they don't know, like they just imitate the next token. They don't know what they're good at or not good at. They just try their best to imitate the next token. They don't reflect in the loop. They don't sanity check anything. They don't correct their mistakes along the way by default. They just sample token sequences. They don't have separate inner monologue streams in their head, right? They're evaluating what's happening. Now, they do have some sort of cognitive advantages, I would say, and that is that they do actually have very large fact-based knowledge across a vast number of areas because they have, say, several 10 billion parameters, so that's a lot of storage for a lot of facts. And they also, I think, have a relatively large and perfect working memory. So whatever fits into the context window is immediately available to the transformer through its internal self-attention mechanism. And so it's kind of like perfect memory, but it's got a finite size. But the transformer has a very direct access to it, and so it can like losslessly remember anything that is inside its context window. So that's kind of how I would compare those two. And the reason I bring all of this up is because I think to a large extent, prompting is just making up for this sort of cognitive difference between these two kind of architectures, like our brains here and LLM brains. You can look at it that way almost.
好，接下来是第二段的解说。比如说，以加州的人口数啊，是阿拉斯加州的几倍这个假设这个问题哈，一个问题，我们要找到答案。那我们通常人呢会做的方法，他举一个例子，就是说我们会去查 Wikipedia 啦，然后用计算机算一下到底数字的倍率啦，算出来我们还会推估一下，这个数字到底合不合理？以我印象中的这个答案对不对？会不会太夸张等等，然后发现错了还会改写啊，重新再把问题修正嘛。那一样的情况，如果是 ChatGPT 啊，他的做法会是因为这个他说 ChatGPT 的行为，其实他就是设计当初训练出来的要求，他就是尽量模仿人类在使用文字产生文字的做法嘛，所以他其实会尽可能模仿出人类的文字的叙述，但是他不知道他自己不懂哪些知识，他也不知道自己不擅长什么，而且他不会反思哦，就错了他就直接输出完，他就完成了一个程式语言，一个 AI 模型要做的事了嘛。但是同时间 ChatGPT 它拥有非常多领域的知识哦，比如说以我们知道的，大概就是50个 terabyte， 目前人类历史上网际网络所有公开可以查的资料，它已经训练进去了，所以它的跨多领域的知识，这个能力应该是一般凡人是达不到的哈。然后他的记忆力非常的棒，那个是 Andrej 这样讲的。但是其实这个我觉得有点不同的想法，就是说以 GPT 3.5 Turbo 啊，你跟他对话，如果你发现来跟回哈，中文字超过1300个的时候，大约啦哈，开始他就会忘记了最前面的那个对话的内容，因为超过了他记忆的限制。 3.5 GPT 3.5大概它就记得1300多个中文字了，超过它就会把最前面那些对话就忘记了哦。但是同时间他讲的Andrej讲的，我觉得也很一部分另外一面很对，在1300个中文字里面，它对应到对话内容，其实它的记忆跟它的处理使用反应是非常快的哈，所以它有这样的一个限制，它有这样的特点，这是人类跟 Chat GPT 的比较。那另外他有提到在这个 part 里面呢，提示工程，他认为其实提示工程如果有另外一个很有趣的比喻哦，就是看起来就是把人脑 AI 脑跟人脑结合起来的一个手段，其实就是提示工程哦，这个蛮有趣的。
So here's one thing that people found, for example, works pretty well in practice. Especially if your tasks require reasoning, you can't expect the transformer to do too much reasoning per token. And so you have to really spread out the reasoning across more and more tokens. So for example, you can't give a transformer a very complicated question and expect it to get the answer in a single token. There's just not enough time for it. These transformers need tokens to think, quote unquote, I like to say sometimes. And so this is some of the things that work well. You may, for example, have a few-shot prompt that shows the transformer that it should show its work when it's answering a question. And if you give a few examples, the transformer will imitate that template, and it will just end up working out better in terms of its evaluation. Additionally, you can elicit this kind of behavior from the transformer by saying, let's think step by step, because this conditions the transformer into sort of showing its work. And because it kind of snaps into a mode of showing its work, it's going to do less computational work per token. And so it's more likely to succeed as a result, because it's making slower reasoning over time. Here's another example. This one is called self-consistency. We saw that we had the ability to start writing, and then if it didn't work out, I can try again, and I can try multiple times and maybe select the one that worked best. So in these kinds of approaches, you may sample not just once, but you may sample multiple times, and then have some process for finding the ones that are good, and then keeping just those samples, or doing a majority vote, or something like that. So basically, these transformers, in the process, as they predict the next token, just like you, they can get unlucky, and they could sample a not a very good token, and they can go down sort of like a blind alley in terms of reasoning. And so, unlike you, they cannot recover from that. They are stuck with every single token they sample, and so they will continue the sequence even if they even know that this sequence is not going to work out. So give them the ability to look back, inspect, or try to basically sample around it. Here's one technique also. You could, it turns out that actually LLMs, they know when they've screwed up. So as an example, say you ask the model to generate a poem that does not rhyme. And it might give you a poem, but it actually rhymes. But it turns out that, especially for the bigger models like GPT-4, you can just ask it, did you meet the assignment? And actually, GPT-4 knows very well that it did not meet the assignment. It just kind of got unlucky in its sampling. And so it will tell you, no, I didn't actually meet the assignment. Let me try again. But without you prompting it, it doesn't even, it doesn't know to revisit and so on. So you have to make up for that in your prompts. You have to get it to check. If you don't ask it to check, it's not going to check by itself. It's just a token simulator. I think more generally, a lot of these techniques fall into the bucket of what I would say recreating our system 2. So you might be familiar with the system 1, system 2 thinking for humans. System 1 is a fast automatic process, and I think kind of corresponds to an LLM just sampling tokens. And system 2 is the slower, deliberate planning sort of part of your brain. And so this is a paper actually from just last week, because this space is pretty quickly evolving. It's called Tree of Thought. And in Tree of Thought, the authors of this paper propose maintaining multiple completions for any given prompt. And then they are also scoring them along the way and keeping the ones that are going well, if that makes sense. And so a lot of people are really playing around with kind of prompt engineering to basically bring back some of these abilities that we sort of have in our brain for LLMs. Now, one thing I would like to note here is that this is not just a prompt. This is actually prompts that are together used with some Python glue code, because you actually have to maintain multiple prompts, and you also have to do some tree search algorithm here to figure out which prompts to expand, etc. So it's a symbiosis of Python glue code and individual prompts that are called in a while loop or in a bigger algorithm. I also think that there's a really cool parallel here to AlphaGo. AlphaGo has a policy for placing the next stone when it plays Go, and this policy was trained originally by imitating humans. But in addition to this policy, it also does Monte Carlo tree search. And basically, it will play out a number of possibilities in its head and evaluate all of them and only keep the ones that work well. And so I think this is kind of an equivalent of AlphaGo, but for text, if that makes sense. So just like tree of thought, I think more generally, people are starting to really explore more general techniques of not just a simple question-answer prompts, but something that looks a lot more like Python glue code, stringing together many prompts. So on the right, I have an example from this paper called React, where they structure the answer to a prompt as a sequence of thought, action, observation, thought, action, observation, and it's a full rollout, a kind of a thinking process to answer the query. And in these actions, the model is also allowed to tool use. On the left, I have an example of AutoGPT. And now AutoGPT, by the way, is a project that I think got a lot of hype recently. But I think I still find it kind of inspirationally interesting. It's a project that allows an LLM to sort of keep a task list and continue to recursively break down tasks. And I don't think this currently works very well, and I would not advise people to use it in practical applications. I just think it's something to generally take inspiration from in terms of where this is going, I think, over time. So that's kind of like giving our model system to thinking.
好，第三段的解说。那第三段呢，他就开始讲到说，如果是要从 ChatGPT 拿到更好、更准确的回复效果，可以怎么做啊？哈，那他就是把那是在目前真的穷举，因为他是 OpenAI 的研究人员嘛，这个应该是很原汁原味的答案哦。第一个可以用思想链，可以用 Chain of Thought， 就是说。提示 ChatGPT 呢，比如说你可以给他一个范例，说我是这样逐步推理才得到答案的哦。麻烦你也跟我一样，新的问题逐步的推理拿到答案，可能准确率可以更高，这是目前知道，而且有论文。有研究报告证明的嘛，好。第二个 assemble multiple attempt， 就是说一样的问题呢，你可以就想象说美国的当初啦，美国的太空梭，它在要飞行的时候，据说飞机上那个太空梭上有3台电脑，同时间在判断我们现在在太空梭该左倾右倾，该加速减速，选出最多台电脑建议的做法，就投票嘛。他说其实可以一样的做法，如果我们问 ChatGPT 问题，我们可以同一个问题问很多次，把这几个问题拿回来，然后最后来票选，或者我们用什么样的方式找出最佳的答案，然后再回复给使用者。那第三个呢是反思，就是说如果你问了 ChatGPT 他回答到你问题了，那你可以问他说这个问题你可以再回问他一句，这个问题真的是正确的答案吗？你能帮我确认一下。他的反思在 ChatGPT 在 GPT-4 啦，就是说在它比较新比较强的模型上，它通常会得到比较好的效果。那另外一个蛮有趣的点，就是说他举了一个例子，就是2022年有一本还蛮畅销的书叫《快思慢想》嘛，对不对 ？Thinking Fast and Slow， 他就把 ChatGPT 来跟那个的怎么样做到系统1跟系统2哈？系统1指的就是说快问快答嘛，直接一个问题一个情境栏，你直接很快速的不假思索用直觉的回复。系统2是说你快思，你知道了这件事了，那你慢慢的逐步的把问题做法慢慢的想出来。他认为呢ChatGPT 是同时可以做到这2种思考模式的哈，事实上也是。那第2种思考模式呢，就可以透过像那个 Android 有举例 AutoGPT 啦，然后 LangChain 或者是 Semantic Kernel 这几个开源的专案，其实目前都可以搭配 ChatGPT 达到这个系统2慢想，就逐步推理得到结果的这个做法。
The next thing that I find kind of interesting is this following sort of, I would say, almost psychological quirk of LLMs, is that LLMs don't want to succeed. They want to imitate. You want to succeed, and you should ask for it. So what I mean by that is when transformers are trained, they have training sets. And there can be an entire spectrum of performance qualities in their training data. So for example, there could be some kind of a prompt for some physics question or something like that, and there could be a student solution that is completely wrong, but there can also be an expert answer that is extremely right. And transformers can't tell the difference between they know about low quality solutions and high quality solutions, but by default, they want to imitate all of it because they're just trained on language modeling. And so at test time, you actually have to ask for a good performance. So in this example, in this paper, they tried various prompts. And let's think step by step was very powerful because it sort of like spread out the reasoning over many tokens. But what worked even better is let's work this out in a step-by-step way to be sure we have the right answer. And so it's kind of like conditioning on getting a right answer. And this actually makes the transformer work better because the transformer doesn't have to now hedge its probability mass on low-quality solutions, as ridiculous as that sounds. And so basically, feel free to ask for a strong solution. Say something like, you are a leading expert on this topic. Pretend you have IQ 120, etc. But don't try to ask for too much IQ, because if you ask for an IQ of like 400, you might be out of data distribution. Or even worse, you could be in data distribution for some like sci-fi stuff, and it will start to like take on some sci-fi like role-playing or something like that. So you have to find like the right amount of IQ. I think it's got some U-shaped curve there. Next up, as we saw, when we are trying to solve problems, we know what we are good at and what we're not good at, and we lean on tools computationally. You want to do the same potentially with your LLMs. So in particular, we may want to give them calculators, code interpreters, and so on, the ability to do search. And there's a lot of techniques for doing that. One thing to keep in mind, again, is that these transformers by default may not know what they don't know. So you may even want to tell the transformer in a prompt, you are not very good at mental arithmetic. Whenever you need to do very large number addition, multiplication, or whatever, instead use this calculator. Here's how you use the calculator. Use this token combination, et cetera, et cetera. So you have to actually like spell it out because the model by default doesn't know what it's good at or not good at necessarily, just like you and I might be. Next up, I think something that is very interesting is we went from a world that was retrieval only all the way, the pendulum has swung to the other extreme where it's memory only in LLMs. But actually, there's this entire space in between of these retrieval augmented models, and this works extremely well in practice. As I mentioned, the context window of a transformer is its working memory. If you can load the working memory with any information that is relevant to the task, the model will work extremely well because it can immediately access all that memory. And so I think a lot of people are really interested in basically retrieval augmented generation. And on the bottom, I have like an example of Llama Index, which is one sort of data connector to lots of different types of data. And you can index all of that data, and you can make it accessible to LLMs. And the emerging recipe there is you take relevant documents, you split them up into chunks, you embed all of them, and you basically get embedding vectors that represent that data. You store that in the vector store, and then at test time, you make some kind of a query to your vector store, and you fetch chunks that might be relevant to your task, and you stuff them into the prompt, and then you generate. So this can work quite well in practice. So this is, I think, similar to when you and I solve problems. You can do everything from your memory, and transformers have very large and extensive memory, but also it really helps to reference some primary documents. So whenever you find yourself going back to a textbook to find something, or whenever you find yourself going back to documentation of a library to look something up, the transformers definitely want to do that too. You have some memory over how some documentation of a library works, but it's much better to look it up. So the same applies here. Next, I wanted to briefly talk about constrained prompting. I also find this very interesting. This is basically techniques for forcing a certain template in the outputs of LLMs. So guidance is one example from Microsoft, actually. And here we are enforcing that the output from the LLM will be JSON. And this will actually guarantee that the output will take on this form because they go in and they mess with the probabilities of all the different tokens that come out of the transformer, and they clamp those tokens. And then the transformer is only filling in the blanks here. And then you can enforce additional restrictions on what could go into those blanks. So this might be really helpful. And I think this kind of constraint sampling is also extremely interesting.
接下来是第4段的解说。所以这边呢，我们也来提的就是说，它Andrej 提到 ChatGPT 它主要呢是训练是在模仿人模仿人使用语言的方式，所以其实这个模型本身啊，它不知道它回答的结果到底对人来讲是好还是不好。虽然在训练过程有持续优化嘛，但是它其实不知道对人当下来讲这个问题到底是好还是不好，对这个情境、对这个区域、对这群人每个人的观感可能会不一样嘛。所以其实你可以在提示工程里面，你可以借由加入说，你就假装你是什么什么领域的专家，那你可以假装你的IQ 就叫 ChatGPT 假装了假装 ChatGPT 你的 IQ 是120，那你这个问题你可以 会提供什么样的回复等等，用这样子来把这个回答的框架范围设定好，那 ChatGPT 就可以知道我们问的人要求的是什么，你就可以拿到更准确或者更好的回答了。这是提示工程的一个可以采用的做法。那另外在这一段影片里面呢，他有另外提到一个 retrieval augmented 就检索增强的这个技巧，意思是说在那个大型语言模型，不管是 ChatGPT 什么，就像我们刚刚讲的嘛，GPT 3.5 中文字呢就只能每次对话它只能记得大概1300多个中文字。那这个记忆是有限的嘛？但是如果我们要询问、要去处理、要对话的内容超过了这么多的字数的时候，应该要怎么做？所以 Andrej 就有提到了，用这种检索增强的技巧，把很多的需要的知识放在向量资料库里面，然后可以用几种开源专案的技术，像里面有提到 LLM Index 等等，把这些资料先储放好，然后 ChatGPT 他发现他需要取得哪一段落的资料拿出来，可以更方便他回答，那他就去把那一段资料找到，然后来回答，补足他的工作记忆是有限的这样的一个限制。
I also wanted to say a few words about fine-tuning. It is the case that you can get really far with prompt engineering, but it's also possible to think about fine-tuning your models. Now, fine-tuning models means that you are actually going to change the weights of the model. It is becoming a lot more accessible to do this in practice, and that's because of a number of techniques that have been developed and have libraries for very recently. So for example, parameter-efficient fine-tuning techniques like LoRa make sure that you're only training small, sparse pieces of your model. So most of the model is kept clamped at the base model, and some pieces of it are allowed to change, and this still works pretty well empirically, and makes it much cheaper to sort of tune only small pieces of your model. It also means that because most of your model is clamped, you can use very low precision inference for computing those parts because they are not going to be updated by gradient descent, and so that makes everything a lot more efficient as well. And in addition, we have a number of open sourced high quality based models. Currently, as I mentioned, I think Llama is quite nice, although it is not commercially licensed, I believe, right now. Some things to keep in mind is that basically fine-tuning is a lot more technically involved. It requires a lot more, I think, technical expertise to do right. It requires human data contractors for data sets and or synthetic data pipelines that can be pretty complicated. This will definitely slow down your iteration cycle by a lot. And I would say on a high level, SFT is achievable because it is just you're continuing the language modeling task. It's relatively straightforward. But RLHF, I would say, is very much research territory and is even much harder to get to work. And so I would probably not advise that someone just tries to roll their own RLHF implementation. These things are pretty unstable, very difficult to train, not something that is, I think, very beginner-friendly right now, and is also potentially likely also to change pretty rapidly still. So I think these are my sort of default recommendations right now. I would break up your task into two major parts. Number one, achieve your top performance, and number two, optimize your performance, in that order. Number one, the best performance will currently come from GPT-4 model. It is the most capable model by far. Use prompts that are very detailed. They have lots of task contents, relevant information and instructions. Think along the lines of what would you tell a task contractor if they can't email you back? But then also keep in mind that a task contractor is a human and they have inner monologue and they're very clever, etc. LLMs do not possess those qualities. So make sure to think through the psychology of the LLM almost and cater prompts to that. Retrieve and add any relevant context and information to these prompts. Basically refer to a lot of the prompt engineering techniques. Some of them I've highlighted in the slides above, but also this is a very large space, and I would just advise you to look for prompt engineering techniques online. There's a lot to cover there. Experiment with few-shot examples. What this refers to is you don't just want to tell, you want to show whenever it's possible. So give it examples of everything. That helps it really understand what you mean, if you can. Experiment with tools and plugins to offload tasks that are difficult for LLMs natively. And then think about not just a single prompt and answer, think about potential chains and reflection and how you glue them together and how you could potentially make multiple samples and so on. Finally, if you think you've squeezed out prompt engineering, which I think you should stick with for a while, look at some potentially fine-tuning a model to your application, but expect this to be a lot more slower and involved. And then there's an expert fragile research zone here, and I would say that is RLHF, which currently does work a bit better than SFT, if you can get it to work. But again, this is pretty involved, I would say. And to optimize your costs, try to explore lower capacity models or shorter prompts, and so on. I also wanted to say a few words about the use cases in which I think LLMs are currently well suited for. So in particular, note that there's a large number of limitations to LLMs today. And so I would keep that definitely in mind for all your applications. Models, and this, by the way, could be an entire talk, so I don't have time to cover it in full detail. Models may be biased, they may fabricate, hallucinate information, they may have reasoning errors, they may struggle in entire classes of applications, they have knowledge cutoffs, so they might not know any information above, say, September 2021. They are susceptible to a large range of attacks, which are sort of like coming out on Twitter daily, including prompt injection, jailbreak attacks, data poisoning attacks, and so on. So my recommendation right now is use LLMs in low-stakes applications, combine them always with human oversight, use them as a source of inspiration and suggestions, and think co-pilots instead of completely autonomous agents that are just like performing a task somewhere. It's just not clear that the models are there right now. So I wanted to close by saying that GPT-4 is an amazing artifact. I'm very thankful that it exists, and it's beautiful. It has a ton of knowledge across so many areas. It can do math, code, and so on. And in addition, there's this thriving ecosystem of everything else that is being built and incorporated into the ecosystem. Some of these things I've talked about. And all of this power is accessible at your fingertips.
好，那接下来是我们第5段的解说。那使用呢 ChatGPT 的建议这就是 Andrej 它对于目前在市面上如果要使用 ChatGPT 公司假设要有系统性的使用的话，它的建议是怎样？它建议是先用 GPT-4。那因为它的回答的效果，它回答的能力是最强的嘛。目前以我们知道，如果以刚刚最前面那个排行榜 GPT-4 就是目前各方各面能力都是最强的语言模型。那然后接着呢，再用各用的刚刚前面提到的各种提示工程的方法，来改善人类希望拿到的成果。然后如果说你需要的是像是刚刚讲需要反思啦，或者需要的回答的资讯来源，除了 ChatGPT 本身可能会知道的常识的资料，也有可能有些是公司内部的特定知识库的资料，你能够透过一些多次呼叫，搭配一些语言工具的方式，像刚刚前面讲的几个开源工具，你就可以让它具备更广、更多的对话的资讯理解跟对话的能力。然后如果前面这些做法都没有办法得到你要的效果，他建议这时候才做 fine tune 再来进行微调，因为他影片里面这一段讲了很多次，他认为微调其实不是一般的人力可以达到的效果，而且有时候可能微调的效果会更差。那第二个使用 ChatGPT 的建议是说，他认为成本节省方面，他认为是说，如果你拿到你要的效果了，用 GPT-4 对不对？步骤1嘛那接下来呢，你就可以试着用 GPT 3.5， 因为它比较便宜，回答的比较快。那用一样的问题、一样的做法去问 GPT 3.5， 看你能不能达到一样或者类似的效果。如果可以接受，那你的成本基本上就可以压到使用这个 OpenAI、使用这个 ChatGPT 的使用成本就可以降到更低 ，CP 值就会更高嘛那最后呢，他在建议使用的情境就是他认为使用的情境上呢，最好是 AI 跟人协作。就是说，而且使用的应用呢，希望是比较低风险的，也就是说，不要跟企业或者是跟业务非常核心相关的。假设万一他的回答有出错，可能会让您的营收有影响等。他建议不要应用在这些相对来讲不要用在太高风险，就是太可能会 AI 如果回答不得体，或者是甚至不正确，或者是甚至是有很多负面语言的时候，可能对您的公司的商誉可能会有造成影响的这个区域，建议先不见得要尝试，然后由人来最后 oversight 来看一下它产出的结果。那第二个呢，他认为可以使用的情境就是如果是创意发想啦，或者是一些方案的建议，用 OpenAI 可以帮我们比如说产生一些我们可能设计比如说一些 proposal 议案的框架等等，这会蛮好用的。 那最后呢，他关于使用这个 AI 的方式，他认为是最好是就是用微软这几个月很多的术语，很多的重复提到字嘛 ，Co-pilot， 它是副驾驶，人跟电脑，人是副驾驶啊，帮忙人我们做更多工作效率的提升，然后更多效率、更多内容的产出等等他不建议用拿 AI 来做全自动的执行，有就是 autonomous agent 他不建议你把它放着，然后就叫做 AI 就是24小时不停的运作，然后做它可能该做的事情，人都不用去管。他认为不建议这样子做。好，所以以上呢就是我们揭露了这几段那个Andrej 他的影片，我们认为这个影片内容真的含金量还蛮高的，然后我们加上我们自己的理解，做一些说明补助上去。那麻烦，如果各位对这个影片内容有任何的意见，也欢迎在 YouTube 下面留言给我们。谢谢大家，拜拜。